Hello, and welcome to this Reigate College Further Maths video for further mechanics, looking at Hooke's law using the formula. So with Hooke's law, this is all about elastic strings and springs. So the difference between an elastic string, that's like a piece of elastic, or a spring, which you all know what a spring is, but a spring can be compressed, and that is the difference between the two of those items. You need to be careful because obviously string and spring are very similar words, and you need to watch out in the question to see which one of those things you've got. Now, we know that the tension in a string or a spring is proportional to the length of the string. So if you stretch it further, there's a greater tension in it. So this leads to Hooke's law, which is that tension is equal to lambda, which is the modulus of elasticity, multiplied by x, which is the extension, divided by L, or A, which is the natural length of the string or spring. So this is the formula, which is called Hooke's law, and that's what we're going to be using. First question, we've got an elastic spring of length 1.4, and it's stretched to a length of 2.2. So a diagram is always helpful, even if it's quite simple. So we stretch it across like that. And we draw in the natural length and also the extended length. So the natural length of this is 1.4. And it's extended to 2.2. So that's an extension of 0.8. And we've got a tension pulling it out that way. And the tension is equal to 16 newtons. So there must be a tension acting back this way, and that's going to be equal to lambda x over L. So writing out the formula, the tension is lambda x over L. And filling in the values we've got, 16, this tension here must be equal to this because the spring is in equilibrium. So that is equal to lambda, which we're trying to find, multiplied by the extension, which is 0.8, divided by the natural length of the spring, which is 1.4. Rearranging that, we're going to get that lambda is 16 multiplied by 1.4 divided by 0.8. And that gives me 28 newtons. So that is the modulus of elasticity for that spring. So it's how stretchy the spring is. Let's look at the next question. We've got an elastic string this time, and this is attached to a fixed point, and a mass of 0.5 is suspended from the other end. So this is hanging vertically like this. We've got a mass of 0.5 attached to one end. So there will be a force down, the weight will be a force down, 0.5 G. That will be matched by the tension in the string because it is in equilibrium. So you can also put your distances on here. The stretch length of the string is 63. So we could mark on here the extension and the natural length of the string. It's worth writing, let the extension be x, so that you've clearly defined what your variables are going to be. So we've got the extension here, and then here we've got 63 minus x, because that is the natural length of the string. So we're now going to use Hooke's law. So we've got that the tension in the string, which must be 0.5 G, 0.5 G is equal to lambda, which we're given is 7, the extension, which is x, over the natural length of the string is 63 minus x. So rearranging that, multiplying this all up, we get 4.9, that's what that is equal to, multiplied by 63, minus 4.9 multiplied by x is 7x. And that gives me 308.7 is 11.9x. and solving, that gives me x is 25.9 centimetres. That's the extension. The question asked for the extension and the natural length of the string. So we need to make sure we answer that as well. The natural length is going to be 63 minus 25.9, which is equal to 37.1 centimetres. Remember, you must only give your answers to 3 significant figures, no more accurately than that, when you've used G in the question. You could do this question all in meters. It is important that you use consistent units throughout Hooke's law questions, but whether you use centimeters or meters, that is your own choice and be guided by the question. So moving on to question 3, we've now got a spring that's in compression. So again, a diagram will help you here. Even if it's only a simple diagram, it just gets you working out what's happening. Personally, I like to draw my springs like that, but you could just draw it as a straight line. It's compressed by a force of 21 newtons. So there's a force of 21 newtons pushing this spring to compress it. There must be then a tension in the spring that's pushing that way, opposing that force, and the tension in the spring is going to be 21. We're told the natural length and we're told lambda, so we should be able to work out the compressed length of the string. Again, let the compression equal x. So we've got the natural length of the spring is 0.4, and we're told lambda equals 70. So the tension in the string is lambda x over L. Filling in the values we know, the tension is 21, its equivalence here, is lambda, which is 70, multiplied by x, which we're trying to find, divided by the natural length of the string, which is 0.4. And this gives me that x is 0.12 meters. Again, have we answered the question? Not quite. It asks for the compressed length of the spring. So the length, we put compressed there just to make it clear that is what we're finding. Length of the spring is going to be 0.4 minus 0.12, which is 0.28 meters. Very important to put the units in because we could have been working in centimeters. Question 4 here, the questions will start to get just a little bit more complicated. This time we've got a string stretched to a length of 38 centimeters when that force is applied. Then the force is increased to 21 and the string's length becomes 46. So we've got 2 different situations going on here that are going to lead to 2 sets of equations, and then we'll solve them together. So let's have a look at what we've got. The first situation, it's stretched to a length of 38. Because of the way the formula works, it is worth starting off with the natural length of the string here, and then showing the extension. So the extension is going to be 38 minus the natural length of the string, because we're told that it's stretched to a total length of 38. This generally makes substituting into the formula easier. There's a downwards force, a force of 15 newtons is applied. So this is on a horizontal, it's not actually being suspended here. So let's apply Hooke's law to this situation here. We've got the tension, 15 equals lambda, which is what we're trying to find. The extension, which is 38 minus L, divided by L. So that's one equation there, and we can multiply up 15L is equal to lambda times 38 minus L. And we'll call that equation 1. Then we're going to have a second diagram over here. This time we've got a force of 21 acting down. So a force of 21, we've got a different tension in the string here. And what else have we got? We've got L is the natural length of the string, which is still going to be the same, but this time the extension is 46 minus L. So here we've got the extension and this tension here. So let's set up the second equation. The tension, 21, is equal to lambda, the natural length, sorry, the lambda x, the extension, which is 46 minus L, divided by the natural length, which is L. So we then have 21L is lambda times 46 minus L. And that's equation 2. Now we've got two equations with two unknowns, so we should be able to solve it. If we do equation 1 divided by equation 2, we're going to get 15 over 21, so the L's will cancel, is equal to 38 minus L divided by 46 minus L. Multiplying up and rearranging, this gives me that 2L is equal to 36, so L is equal to 18 centimetres. It also asks for the modulus of elasticity, so we're going to substitute it back into one of these equations here. So substitute back into equation 1, and we get that lambda is equal to 15 times 18 divided by 38 minus 18, and that gives me 13.5 newtons. One final question now to do. We're going to look at question 5 here. Question 5, again, starting to get slightly more complicated. So what we've got are two elastic springs joined to form one long spring. The natural lengths of the springs are 0.8 and 1.2, and we've got the modulus of elasticity for both of them. They're attached 3 meters apart. So that means both springs will be in extension. And it says to find the length of the combined spring. So we're going to draw a nice clear diagram showing what's happening. We're going to join here, and we're going to have a tension in one spring, and a tension in the second spring. We've then got this going on underneath. The natural length of this first one is 0.8 plus its extension, and that's going to take me to the join. And then here we've got 1.2 plus an extension, which we're going to call y. So we've got 0.8 plus x for the first spring and 1.2 plus y for the second spring. And all of this is equal to 2. Beg your pardon, is equal to 3 because they are 3 meters apart. So let's just have a look at what equations we can form from this. So we've got that 0.8 plus x plus 1.2 plus y is equal to 3. So that gives me x plus y equals 1. So that's my first equation. We're then going to consider that they are in equilibrium here. So we know that the two tensions are equal. Let's have a look at what those tensions are using Hooke's law. The tension for the first spring is lambda. So T1 is going to be lambda for the first spring, which is 18, x over the natural length, which is 0.8. And that must be equal to the same equation for the second spring, which is going to be lambda, which is 21, times the extension, which is y, multiplied by 1.2. So multiplying this equation up here and solving it, we get that 21.6x is 16.8y. And if we substitute in 1, so we substitute this into equation 1, so sub in equation 1, we're going to get 21.6x is equal to 16.8 times y, which is 1 minus x. And when we solve this equation, we get that x is 7/16. Question asks you for the tension, so we need to substitute that in and find the tension. And the tension is going to be 18 multiplied by 7/16, or divided by 0.8, which gives me 9.8 newtons. So that is the tension in the combined spring. So you need now to have a look at questions in exercise 3A and practice using Hooke's law.